Assalamu alaikum dear students. I hope you are all fine by the grace of Almighty Allah. I welcome you all to the 8th lecture of Thermodynamics 2. Lecture 8. Contents of Lecture 8 are work and heat transfer for open systems. Work and heat transfer for various processes. These processes include isobaric process, isochoric process, isothermal process, adiabatic process, and polytropic process. Then we will solve some numerical problems and we will go through some conceptual questions and answers. Work and heat transfer for open system. Now we will derive a relation for control volume work WCV for open system, and then we will utilize that relation to derive heat transfer equation for different processes according to steady flow energy equation. So the steady flow energy equation is mentioned: Q is equal to H1 plus C1 square by 2 plus GZ1 is equal to W control volume plus H2 plus C2 square by 2 GZ2. Q is the heat interaction between system and environment. H1 is the enthalpy of the fluid at the inlet. C1 square by 2 is the kinetic energy component at the inlet. GZ1 is the potential energy component at the inlet. WCV is the controlled volume work done. H2 is the enthalpy at the exit plus C2 square by 2 is the kinetic energy component at the exit. GZ2 is the potential energy component at the exit. So for reversible ideal gas and closed system, the relation for work done is W is equal to integration P dV. So you should remember that this is the relation for closed volume work done, closed process, work done for the closed process, and it should be reversible and for ideal process. Now we have retained the Q term on the left hand side, and other factor we have moved to the right hand side in the steady flow energy equation. So change in enthalpy is the first term, change in kinetic energy, and change in the potential energy plus control volume work done. So we have written all these into the differential term. Change dH is the change in kinetic energy, dk is change in kinetic energy, dH is the change in the enthalpy, dk is the change in the kinetic energy, dP is the change in the potential energy. Now we have derived two relations for the enthalpy that are also known as the Gibbs relation. So we have previously derived those relation. dH is equal to du plus pdv plus vdp. So the main is H is equal to u plus pv. When we differentiate left hand side and right hand side, so it will be dH is equal to du plus, here there will be a product rule, so first derivative of second plus second derivative of first, so that is here is written p dv plus v dp, and dq is, you know that from first law of thermodynamics, dq is equal to du plus w, and closed volume work done is written as p dv. So we have replaced the w with p dv. So dq is equal to du plus p dv. So in the upper equation, du plus p dv will be replaced by dq. So that term and that term is same, so we will equate it with dq will be moved up. So here we have replaced it with the dq term, and the right side term will remain the same. So dq will be cancelled out, and the term left will be W control volume change kinetic energy change potential energy is equal to minus integration V dP. For change in kinetic energy and change in potential energy is negligible, then the terms containing kinetic and potential energy component will be cancelled out, and control volume work done for open system is given by minus integration sign V dP. So the graph for closed system work done is on the left hand side, and the PV graph for open system is on the right hand side. Heat and work transfer for various processes for open system. So we will derive relation for heat transfer and work transfer for various processes for open system. So for first one is isobaric process. So isobaric process is a constant pressure process. I will write it constant P. So work transfer for isobaric process is 0. Why? Because P is constant, then dP is equal to 0. So the work transfer for open system is given by W is equal to minus integration V dP. So as dP is equal to 0, therefore W is also equal to 0. Now steady flow energy equation is given by in the next step. For change in kinetic energy and change in potential energy are negligible, then the kinetic and potential energy component in the steady flow energy equation will be cancelled out, and the WCV is W control volume work done for the open system is also 0. We have just calculated it here. W is equal to 0. When we will insert all these values in the steady flow energy equation, then the heat transfer for isobaric processes Q is equal to H2 minus H1. Now for isochoric process. So what is isochoric process? It is a constant volume process. So control volume work done for open system is given by W is equal to minus integration V dP. So as the in the isochoric process V is constant, so it will come out of the integration, and we will integrate the term W is equal to minus V P2 minus P1 is the change in the pressure. So as V is constant, so we will multiply V with both. So Vp2 minus Vp1. So V is constant, so we will write the first one with the first term and V2 with the second term. So W is equal to P1 minus P1 V1 minus P2 V2. So from ideal gas equation, you know that PV is equal to RT. So V is the specific volume. So for P1 V1, that will be RT1. Okay. So temperature at the inlet minus temperature at the outlet. W is equal to MRT1 minus T2. So for isochoric process, the first relation is the steady flow energy equation. Steady flow energy equation for change in kinetic and potential energy negligible. Q plus H1 is equal to WCV plus H2. Now in the previous slide, we have found that the control volume work done for open system for isochoric process is P1 V1 minus P2 V2 in the previous slide. So we will insert the value of work done in here. So Q is equal to, we will move the H1 term to the right hand side and separate the inlet and exit properties. So here we know that H is equal to U plus PV, which means U is equal to H minus PV. We have utilized this relation and convert the enthalpy and pressure volume term into the internal energy. So heat transfer in isochoric process for open system is equal to the change in the internal energy. Now for isothermal process, what is the isothermal process? It is the constant temperature process. So the control volume work done for open system is given by integration sign minus V dP from ideal gas equation. PV is equal to mRT and for isothermal process, right hand side, because the temperature is constant, therefore the right hand side complete will be constant. Now here we have replaced the constant sign term with the C. So C is equal to mRT. V is equal to constant over P, or specific volume, volume is equal to C over P. So that PV is equal to mRT. M is divided on the left hand side, it will become specific volume, and we have replaced the specific volume with C over P. That is specific term, so we have replaced it with C over P. Now C is a constant, therefore it will come out of the integration sign, and the term left is integration 1 over P dP. So as you know that the integration of 1 over x dx is natural log of x, therefore the integration of 1 over P dP is the natural log of P, where 1 and 2 are the limits of integration. When we put the limit of integration, then the answer will be natural log P2 minus P1. We will use the property of log, natural log here, and divide it with the natural log P2 divided by P1. Here that is written. We have used the property of log. So WCV is minus C natural log P2 over P1. Now you know that C is here, C is equal to PV. So we have replaced the C with the that written. So C with the PV. So we have replaced C with P1 V1. So the product will remain constant. So either you can say that it is P1 V1, P2 V2, all values are same. So we have replaced the term C with P1 P1, and natural log P2 over P1 will remain same. So now you should know that we have invert, denominator will come into numerator and numerator will come into the denominator. We have inverse this fraction, therefore negative sign will come out, because this is a log, so therefore you have to minus sign will be multiplied in the inside. So let me show you that. So we have equation minus P1 V1 natural log P2 over P1. So it will minus sign will be multiplied. You can write this in the form P1 V1 natural log P2 minus P1. So there will minus sign, there was minus sign when you have multiplied it. P1 V1 natural log P1 minus P2. So it will be written as P1 V1 natural log P1 over P2. So we have changed the, so P1 will go up and P2 will come down. So control volume work done for open system for isothermal process is P1 V1 natural log P1 divided by P2. Now we will find heat transfer term. So that relation we have find it in the previous slide. So as for isothermal process, PV is equal to constant. So all the value P1 V1 is equal to constant, P2 V2 will be constant, and P3 V3 and so on. So you can compare any value. Therefore it is written P2 over P1 is equal to V1 over V2 here. So we have utilized this relation and derived the control volume work done for open system for isothermal process in term of specific volume. So the pressure term is replaced by specific volume. Here you can see that V2 over V1. So that is a steady flow energy equation. So for change in kinetic and potential energy negligible. So for solving it for heat transfer, Q is equal to H2 minus H1 plus WCV. So we are converting the enthalpy relation into the temperature. Q is equal to Cp T2 minus T1 plus, that is the relation we have found in the previous slide, that is the control volume work done for open system for isothermal process. And for isothermal process, the term T2 minus T1 will be cancelled, is equal to, because that is a constant temperature, therefore that term will be cancelled out, and Q is equal to P1 V1 natural log P1 by P2. Therefore heat transfer for open system for isothermal system is equal to work transfer for open system for isothermal system. Isothermal process, both Q and W for open system are same. Now we will solve it for adiabatic process. The relation for adiabatic process is given by PV gamma is equal to constant. Now what is an adiabatic process? You know that there is no heat interaction between system and surrounding, so Q is equal to 0. So representing the constant term with C, so the specific the value of specific volume is C over P power 1 over gamma. So it has a power gamma. When the power comes out on the right hand side, we will divide it with gamma. So the power of specific volume will be 1 and the power of C over P will be 1 over gamma. So the general expression for work done for control volume for open system is given by WCB is equal to minus integration V dP. So we will replace this specific volume in the general relation with the specific volume term for specific for adiabatic process, C over P power 1 over gamma dP. Now as C is the constant, therefore it will come out of the integration sign on the left side, and the term left in the integration sign is 1 over p power 1 over gamma into dp. So when we will transfer from denominator to numerator, the sign of the power will be negative, will change from positive to negative. So WCV is equal to minus C power 1 over gamma integration sign P power 1 over minus 1 over gamma into dP. In the next step, we have integrated the term in term of P, and we have used the power formula for integration. So in the power, 1 will be added and the complete term of power will be divided by. So minus C power 1 over gamma into P minus 1 over gamma plus 1 and divided by minus 1 over gamma plus 1. 1 and 2 are the limit of integration. Now in the next step, we have inserted the limit of integration. So we have P2 and P1 and the power remain the same. So here we have taken the LCM in the denominator. So 1 minus gamma minus 1 divided by gamma. So we have transported in the left hand side, and we have multiplied the C term into the bracket. So gamma over gamma minus 1 P2 power 1 minus 1 over gamma into C power 1 over gamma minus P1 power 1 minus 1 over gamma into C power 1 over gamma. Now the general relation for adiabatic process is P1 V1 gamma is equal to P2 V2 gamma is equal to constant, and for constant here we have represented with the symbol C. So we will replace the C term with the respective pressure volume term. For here C is replaced by P2 V2 gamma, and the power of the term of C is 1 over gamma here shown. And for the second C, because they both are equal to each other, therefore here C is replaced by P1 V1 power gamma, and the power of the C is 1 over R, that is 1 over R. So I will write this step. So the step here is I will solve this term P power 1 minus 1 over gamma into P2 power 1 over gamma, because that is a power, it is both for P2 and V2. And when we will say that V power gamma multiply 1 over gamma. So when we add, P is the base is common, so 1 minus 1 over gamma plus 1 over gamma into V. So they will multiply, they will cancel out. So P power 1 and P power 1, because they both will cancel. P power 1 P1 V1. So that is written P1 V1 and P2 V2. That term will be reduced. So the minus sign was multiplied inside, and the initial term was P2 V2 minus P1 V1, and minus sign was multiplied inside. So the term is P1 V1 minus P2 V2. So the control volume work done for open system for adiabatic process is equal to gamma over gamma minus 1 into P1 V1 minus P2 V2. Previously, we have found out in lecture 3 and 4 the work done for closed heat transfer and work done for closed system as well. So by remembering from the previous lecture, we found that control volume work done for closed system for adiabatic process is given by 1 over gamma minus 1 into P1 V1 minus P2 V2. Comparing both control volume work for open closed system for adiabatic process, we found that control volume work done for open system for adiabatic process is equal to gamma into control volume work done for closed system for adiabatic process. As gamma is greater than 1, therefore control volume work done for open system and for adiabatic process greater than control volume work done for closed system for adiabatic process. Now we will find heat transfer work done for polytropic process. So you know that polytropic process is a general process which lie between isothermal and adiabatic process. So generally, if you replace the gamma, that is adiabatic constant, with n, that is the polytropic constant. So we know the general form of steady flow energy equation, and if we assume that change kinetic energy and potential energy is negligible, then the reduced form of steady flow energy equation is given in the next step. So Q is equal to H2 minus H1 plus control volume work done. Now control volume work done is found in the previous slide. We will convert the adiabatic control volume work done for open system for adiabatic process will be turned into the control volume work done for the polytropic process. So we have replaced the gamma term with the n. So that is the control volume work done for open system for adiabatic process, that is gamma over gamma minus 1 into P1 V1 minus P2 V2. When we replace it with the n, then it will become n over n minus 1 multiply P1 V1 minus P2 V2. And H2 minus H1 was replaced by MCP T2 minus T1. H is in the form of T. So CP, we have two relations, CP minus CV is equal to R and gamma is equal to CP over CV. When we will combine both these equations, I will write it in the, we have Cp minus Cv is equal to R and gamma is equal to Cp over Cv. When we will combine both these equations, we will find that Cp is equal to gamma R over gamma minus 1. So Cp is written in the term of gamma R over gamma minus 1. All other parameters remain same. So P2 V2 is equal to MRT2 and P1 V1 is equal to MRT1. So here PV terms are reduced in MRT2 minus MRT1 terms. So Q is equal to minus gamma over gamma minus 1 into P1 V1 minus P2 V2 plus N, that is the control volume work done for polytropic process. So the value of heat transfer for polytropic process is P1V1 minus P2V2 over n minus 1. So we have taken the common term P1V1 minus P2V2 common and other terms in the bracket. So n minus 1 is in the denominator, bracket is gamma minus n divided by gamma minus 1. That is the value of heat transfer for open system for polytropic process. So by comparing the heat transfer for open and closed system for polytropic process, we found that both the value of heat transfer for open and closed system for polytropic process are equal. Now we will solve a numerical problem, refrigeration. As one mode of operation of air conditioner is the cooling of a room on a hot day, it works as a refrigerator. A total of 4 kilowatt should be removed from the room, a room at 24 degrees centigrade and the outside atmosphere is 35 degrees centigrade. Calculate the magnitude of work done. So we have a refrigeration system or an air conditioner system installed in a room. So the outside temperature is 35 degrees centigrade and the inside temperature is 24 degrees centigrade. We have to maintain the temperature, and a total of 4 kilowatt should be removed from the room at 4 degrees centigrade. So Q is given. Q dot that should be removed is 4 kilowatt. That will be minus Q. So minus. So the coefficient of performance in the book is mentioned by beta. So beta is the desired effect divided by work input. So desired effect for refrigeration is the Q dot L. So I will briefly, we have two reservoir TH, that is a refrigeration system, and TL. So for refrigeration, work is input. So QL is the amount of heat that is taken out from the low energy reservoir, and QH is the amount of heat transmitted to the high energy reservoir. So the desired effect is to maintain the QL. So W is equal to QH minus QL, and QL in the numerator will remain same. We will transform the Q terms into TL, and the low temperature is 24 degrees centigrade and the high temperature is 35. So value of beta is 27. Coefficient of performance is 27. So the rate of work or power input will be W dot is equal to QL divided by beta. QL is the heat removed from the room, that is 4 kilowatt. So 4 divided by 27, the rate of work or power input is 0.15 kilowatt or 150 watts. So there are some conceptual questions. A temperature difference drive a heat transfer. So you know that you have two bodies. One body is at high temperature TH and other body is at low temperature TL, and if they are joined by some mean or conductor, then heat will be transferred from high temperature to low temperature. The direction is given by this arrow. So the question is, does similar concept apply to the mass flow rate? So that question was asked in the previous lecture by a student, so I have decided to incorporate it in the lecture as well. So the answer is yes, a pressure difference drive the flow. So pressure difference delta P is responsible for the flow driven system. The fluid is accelerated in the direction of lower pressure. So if the direction of flow is from left to right, fluid is flowing from left to right, then P1 is the pressure at the inlet should be high, and P2, that is the pressure at the exit, should be low. So if that pressure delta Tp or pressure difference is maintained, then pressure of the fluid will be different and the fluid will move from 1 to 2 state. If the P1 becomes equal to P2, then the fluid will stop flowing from 1 to 2. So the similar concept is, if you have two bodies and that both bodies should be conductive. So in heat transfer body there should be conductive body should be used for heat transfer as well. So if we have body A and B, body A is at high voltage, VB is at low voltage, then there will be a current or charge flow. So all these concepts are same on the based on the same principle, that there should be some differential in the properties for a flow to be derived. Next conceptual question: which one of the properties PVT, pressure, V specific volume, T is temperature, can be controlled in a flow, and how? So there is some flow, a fluid is flowing through a pipe, that is a pipe, and that is one inlet and two is at the exit. So there will be some pressure at P1, temperature T1, and specific volume. If the mass flow rate is constant, so a fluid is flowing through the pipe, and the exit properties will be P2, T2 temperature, and V2 specific volume. So since the flow is not contained, as that is an open system, so there is no direct control over the volume, therefore volume is uncontrolled. Okay. So we can say that volume is not controlled. However, the pressure can be controlled by installation of a pump or a compressor. So if you want to control pressure, you should install pump or a compressor. Usually these devices are used to increase the pressure if you want to increase it. So pump and compressor are used to increase the pressure, and if you want to decrease the pressure, nozzle or turbine is used. So we have discussed about the nozzle, in which velocity is increased, V2 is greater than V1, and pressure P2 is less than P1. So pressure is decreased in the nozzle. So if we want to increase the pressure, we will use pump and compressor, and if we want to decrease the pressure, we will use turbine and nozzles. And the temperature can be controlled by heating and cooling through heat exchanger. So we have discussed about the heat exchanger in the previous lecture. And so if you want to heat the fluid, so we will introduce a high energy fluid, so heat will be exchanged. So there is a shell, one fluid is moving in the shell and the other fluid is moving in the pipes or tubes, that is known as tube bundle. So if we want to increase or decrease the temperature, so we will use heat exchanger. So the next conceptual question is, a storage tank for natural gas has a top dome that can move up or down. So here is an animation of a tank whose top dome or top surface is movable. So one surface is fixed and the other is moving. So that is the leg. You can see that is the leg, and the surface or the top dome is moving. So a storage tank for natural gas has a top dome that can move up or down as the gas is added or subtracted from the tank, maintaining 110 kilopascal pressure and 290 Kelvin temperature inside. So the temperature at the inside is 110 kilopascal and 290 Kelvin temperature, and a certain pipeline is connected with the tank and its pressure is also 110 kilopascal. So that is the scenario. So a pipeline at 110 kilopascal supplies some natural gas to the tank. Does it change the state during the filling process? So it is asking if a pressure line at is a pipeline at a pressure 110 is connected to a tank containing natural gas which is also at 110 kilopascal pressure. So during filling process, does the state is changed? What happened to the flow work? So I hope you have understand the scenario. So the answer is, as the pressure inside the storage tank is the same as in the pipeline, so the pressure inside the tank is also 110 kilopascal and the pressure in the pipeline is also 110 kilopascal. The state does not change. So you should remember, if there is a filling process and the pressure remains same, then the state does not change. However, the tank volume goes up and work is done on the moving boundary. So the moving boundary is the upper dome of the tank that you are seeing moving up and down. So that is the moving boundary of the tank. So as the gas is flowing through the pipe into the tank, so work is done, boundary work is done. So volume of the tank is increasing. So tank volume goes up and work done on the moving boundary at the 110 kilopascal pressure. So this work equal to the flow work. The net effect is the flow work goes into raising the dome. So the work is net effect is the flow work goes into raising the dome. The flow work is equal to work done to raise the dome. So two things you have to remember, the state is not changed and the work done will equal to the flow work will be equal to the work done for raising the dome. So that is the end of lecture 8. Home assignment, all students are advised to go through example problem for each topic discussed in the lecture. Please submit handwritten reports of the lecture summary at my email address, that is arslan@cietwa.edu.pk. All students are advised to keep hard copies of every assignment and report as they have to submit them later when you will come for the examination at university. All students are advised to prepare previous lecture thoroughly before online video session as there will be a viva and oral answer question session for every student. Thank you very much.